Howdy. In this video we're going to talk about a physical pendulum. Now if you remember, the omega of a physical pendulum is the square root of mgd over I, and so since your period is 2 pi over omega, it's going to be 2 pi times the square root of I over mgd. Now I is a moment of inertia, m is the mass of that object, g is your acceleration due to gravity, and d is really important. D is the distance from the center of mass to the axis of rotation. Very important that you understand that. And so let's take a look at number 1. Number 1, it says that a 1.8 kilogram monkey wrench, so I know that M is 1.8 kilograms, is pivoted 0.25 meters from the center of mass. And so D is 0.25 meters. And is allowed to swing as a physical pendulum. The period of motion is 0.94 seconds. Part A, what's the moment of inertia? Well, taking a look at my equation, let's do a little bit of algebra. We know that T is equal to 2 pi times the square root of I over mgd. So if you want to solve for I would divide by 2 pi, square it, and then multiply by mgd. And so let's plug in all of our numbers. Our t is 0.94 seconds divided by 2 pi, and I would square that, times my mass of 1.8 kilograms, times g, I'm assuming we're on Earth, so 9.8 meters per second squared, times d at 0.25 meters. And so for this, for a moment of inertia I would take the 0.94 divided by 2 pi, and then we're going to square that, times 1.8 times 9.8 times 0.25, and you get 0.09, we'll go with 0.01. So 0.01 kilograms in the meter squared. And now that I have that, in part B, if a wrench is initially displaced 0.4 radians, okay, so we're going to initially displace this wrench, theta, where theta equals 0.4 radians, okay, from its equilibrium position, so that's just hanging down low. What is the angular speed of the wrench? Make it F is what I'm looking for as it passes through equilibrium. So what I'm going to do here is I'm going to utilize conservation of energy. So this will be my H naught, and it's this omega F at the bottom that I'm looking for. Now as for H naught, I know everything's going to be revolved around the center of mass. Everything's revolved around the center of mass. So this right here, I'm going to consider this the center of mass. And here is your axis of rotation. So as it swings down, this length is going to be, it was 0.25 meters. Now, we also know that this length right here, as it swings down, is still 0.25 meters. And so, if you want to find H naught, use this right triangle, what do you think this distance is going to be? This distance right here, this is going to be your 0.25 cosine theta because it's adjacent to my angle. Therefore, your H naught is going to be the 0.25 minus the 0.25 cosine of 0.4 radians. Make sure your mode is in radians, which mine is. So we're going to go 0.25 minus 0.25 cosine of 0.4 radians, and I get 0.02. So I'm going to say that H naught is 0.02 meters. That is my H naught. And so now that I have that, use conservation of energy. if I know that E naught equals EF, initially it's starting at rest, so all your energy is potential. And at the end, it's all going to be kinetic, more specifically rotational kinetic energy. So it'll be 1/2 I omega F squared. And so setting these two equal to each other, mgh naught equal to 1/2 I omega F squared. If we did a little bit of algebra to solve for omega F, this would be the square root of 2 mgh naught divided by I, which would be the square root of 2. We know that my mass is 1.8 kilograms. I'm assuming we're on Earth, so it's 9.8 meters per second squared. H naught we found to be 0.02 meters. And our I we found in part A to be 0.01 kilogram meters squared. And now let's throw all of this into our calculator. And so this is going to be 2 times 1.8 times 9.8 times 0.02. We're going to divide that by 0.01 and then take the square root. And so we're going to get 8.4. And so your omega F is going to be 8.4 radians per second. And this is how you're going to deal with physical pendulums.